Um, Hi, I'm going to tell you about our effort in formalizing distributed deadlock detection. My name is Radosław Rowicki. I come from the Technical University of Denmark, and this work is shared, of course, my supervisors, Alceste, Scalas, and Adrian Francalanza. So what we're doing, we are formalizing and verifying distributed deadlock detection via monitors in a black box manner. So monitors are like attached to each service in a network, and they don't look up into the internal states of services, and they try to altogether make a verdict whether a deadlock occurred as the system is running. So it's dynamic verification. The algorithm itself is not new. It's highly inspired by existing research. But we formally specify all the semantics, syntax of the calculus, and state our goals as soundness, incompleteness, and everything has been mechanized in Coq. So what a deadlock is? What is a deadlock? Everyone knows what a deadlock is. It's just a fancy word for a circle. But in different settings, deadlocks look differently. For example, this is a deadlock in Warsaw. It looks like a square, if not something else. But we don't do traffic jams. We do distributed systems, which are modeled as message passing systems. So a deadlock would look more like you have some services receiving some requests, then making blocking calls to each other, which then suddenly become dependent on each other's dependencies, and bam, you have a circle, right? So what is a service in our case? So we model services as triplets, in heart of which there is this process which describes the encode state of what's happening inside. We focus on Erlang generic servers. If you don't know what that is, it's just design pattern of a service which receives calls and replies to them. And while working on such a reply, it can also make blocking calls to other services. The other items in the structure are input and output queues, so that we have asynchronous receives and asynchronous sends, so there's less like blocking operations inside. Oops. Then if you want to apply monitoring to it, like to construct a monitoring service, monitor service, you essentially isolate such a service from the network, put this guy, this is a monitor, this is our boy, which oversees the communication and acts as a proxy between the service and the rest of the network. So if you have an incoming message, it lands in the monitor queue first, then it is passed to the monitor and forwarded to the service. And the monitor can use this information to update its state and also communicate via special messages called probes with other monitors to communicate the global state. And of course, it works similarly the other way around. So if the service wants to send something, it has to go through the monitor as well, and the monitor also gets a chance to engage in communication, to consult the situation. So an important property of such monitoring is transparency, which we describe as operational correspondence. It is divided into completeness and soundness. Completeness says that if you have a system and apply monitoring to it, then wherever the system goes, the original system would go to whatever state, the monitored one would also be able to reach an equivalent state. So we don't, in a way, monitoring does not inhibit any behaviors. Soundness says that to whatever state you go, you go in the monitor system, we can always continue to one which is corresponding to one if monitoring was not applied. So we don't add spurious behaviors, in other words. Once a deadlock occurs, it has to be detected somehow. And it's the algorithm, in short, works by monitors detecting that a request comes while it is locked, and then it initiates a cycle seeking procedure, which works it replies with a probe, and this probe is propagated across the dependency graph. So if it returns and the monitor has not observed being unlocked in the meantime, it just raises an alarm because a cycle is evident. Fun fact, if you do this propagation the other way around, then it's unsound. Results, proofs left as an exercise for the machine, because everything has been successfully mechanized and proven in Coq. both statements and everything. I think the results are pretty neat. These are exactly the same statements you saw before, just with fancy cock notations. Behind this beautiful face, you have very, very ugly invariants, which constituted most of this work. And I'm not going to show them to you because they're just too big. I don't have time. I guess you're itching to see how this process works, because that's something I did not distract while talking about it. So processes are described as co-inductive constructions. This is the sort of syntax with three constructions. One is tau, which means that it's an internal action, just process does something internally, wasting time. You can send a message to someone and this message to someone and proceed to this process. And receive is where some trickery is happening, because normally you would describe calculus purely inductively with an explicit like variable object stored here, but I saw a continuation here, sort of breaking the decorum between syntax and semantics, because here you have a function which is able to select a message and optionally proceed differently depending on what the received value is. That might look weird, but it has several different advantages, because this allows me to program processes directly in Galena. So I don't have to specify semantics for stuff which are completely not interesting from the perspective of like programming distributed systems, such as pattern matching, ifs, and all that lambdas and all that stuff. That's just left for the Galena side. Another good thing is that normally you would have a binder here in the receive operation, and here I just delegated to cock. It handles entirely it for me, and well, that's a very, very good thing, because binders are notorious for being completely horrible, and I have citations for them being bad. Final thing is that having it co-inductive lets me do recursion without having to bother for define processes recursively, which is very, very handy. And in the end, the result is that I can program. I developed a program. I developed a framework for programming generic servers, almost like you would do in Erlang. So this is cock, Galena. This is Erlang, and they implement the same service. So these two pieces of code, whatever they do, they look very, very similarly. Like you can't tell which one is uglier. And that's all about deadlock detection. But I've been asked by some reviewers to tell you some lessons learned. So yeah, I'm doing PhD on this project, so surely I learned something. The first lesson is to write your proofs reflexively, because otherwise I would just suffer tremendously if I didn't go for this type. So reflexive proofs are ones in which you refer to types or logical statements instead of the values of these types. So you let automation do the job, and the proof looks more like reflects your reasoning way, way better. So here you have this, I don't know, consider tactic, which brings up and also proves the statement. It also unpacks it, so I can refer to this n prime in other statements. You can read it. This is nice. Yeah, do your proofs like that, and especially don't prove like this. You know, this rage proving, which where you just refer to whatever you can. Suddenly you click QED. It's proven. You don't have to look at it anymore. And yeah, Coq incentivizes you to write stuff like that, and that works until you have to change something. Then, let's say whenever you refer to an auto-generated term, you lose 1 point. And if that term is in prop, you lose 10 points. I know I'm not discovering America here. That's obvious that you just shouldn't write shitty code, but I just want to publicly impose guilt on you if you do this. That's my preaching here. And so how do you write automation which helps you doing proofs like that? Well, use LTAC2. It's okay. I know the other languages. Maybe I should say don't use LTAC1, because if you don't know what LTAC1 is, that's been mentioned before, but it's the default tactic language for Coq, and it works for teaching toddlers dependent type theory. But if you want to do something seriously, LTAC2 is better almost in every case, due to its more concrete semantics. Like it's just well tidied up. On many, it's just faster. Everything is better, except maybe documentation, which is quite lacking, and standard library. Sometimes certain things are missing, but then you can easily call LTAC1 from it. And how much time? Oh, well, you can easily call LTAC1 from LTAC2. And also, we can add stuff to LTAC2 very easy. Like, I recently missed some tactic, and they just made a pull request. The process is very nice. The code is very good to do this. It's very easy to improve it. So I encourage you all to make LTAC2 great for the first time. And that's it. So summarizing, we formalized, implemented, and verified black box monitors for distributed deadlock detection. We post our statements like soundness and completeness properly as it should be done, which is something we didn't see in existing research, frankly speaking. Everything is mechanized, and maybe I should say something about future work while generalizing it. That's it.